Okay, so hello everyone. Welcome back to the seventh section. So today the topic will be quite exciting. We're gonna start to discuss some of the nonlinear solver, and the focus for today will be the Newton-Raphson's implicit solver. So this is a solver that is really widely used in capturing the behavior of shape morphing structures and also many active and adaptive systems, and it's capable of capturing the geometrical nonlinearity and also the material nonlinearity. It's a pretty good method it's a go-to method for many of the problems out there. So before we get into how this method is formulated, however, I do hope to spend some time just to briefly review what the kind of nonlinear solution methods that we've been using in the undergraduate mechanics classes. Right, so this first equation, I hope you are not too unfamiliar with it. If we want to, find the most representative equations for mechanics, that's probably that one, right? The force vector equals to a stiffness matrix times your deformation vector. So this is probably the most iconic equation that represent mechanics. So typically, we know that in most of the cases, the force is given, the stiffness is given, and we're gonna need to solve for the U. So it's kind of that's the more common problems we were asking engineering applications, right? So for instance, if I'm a civil engineer, I might have a building, two-story frame, and then the load from the winds would be F1, F2, and I'm gonna be curious about what kind of a drift I'm having in the building, right? That's a pretty typical problem. So we are curious about the deformation. We know the load. And the same thing for the aerospace or mechanical engineering people, right? Let's imagine that you have a wing, and then this particular wing probably needs to see some forces and load from the air because it's trying to help a plane staying up in the middle of in the high altitude, and to support that we need some it's gonna deform under these applied forces. And for instance, this wing deformed to this location, and we need to know what kind of deformation is happening at the tip so that we can judge whether or not this wing is a good design or not, just like the case in civil engineering, right? So in order to handle that, the way we're going to be doing is just reversing it. If we know the K's and also the F, we can solve a linear system or basically inverse that matrix, and that will give us the U to be K inverse F. Right, that's what we've been doing since undergraduate, the first mechanics class. So most likely we're not going to be actually inversing that matrix because we know computationally it's not very efficient. So we try to solve for a linear system of equations to find the u's from the force. So that's what we've been doing. So that's the equation. And to evaluate how well this type of a linear solution works, let's actually start with this very simple example with just three node and two spring. And I have two springs. One is horizontal, one is vertical. The three nodes are I, J, K. And I try to apply a upward force at the node J with the unit of 1 Newton. And let's try to see what kind of deformation I can find with this type of a linear approach. Right. So this is how we're going to set up that linear solver. And we'll be just using all the equations and all the functions we previously derived in the section 5 and section 6 for the stiffness matrix assembly. We now have two bars. So I create a node from the elements node. That's a stock element we have in these package. There's just three nodes, so this setting up it would be very easy. Node 1 or node I, node J, and node K, right? That's here nodal coordinate. So for the bar, it's also going to be easy. I create a class, create the object. It's going to be just two, right? 1, 2 is the first bar, and then 2, 3, JK is the second bar. And let me set everything to be 1 for the material constant. So keep it simple. So in this case, the one applied load will be actually quite large. So the bar stiffness here is also 1 because I'm setting Young's modulus and also the cross-section area to be 1. Um, so it's actually going to generate some sort of very decent large deformation out of it. So let's see what we get. So the stiffness matrix, we're gonna, because the bar is not yet deformed, we don't know what's the deformation yet, right? So the U would be 0. So just in general, for a system that can experience large deformation, we typically have its stiffness to be calculated based on its deformation matrix, right? So remember in the previous section when we do the stiffness matrix assembly, we always have some sort of a deformation included when we calculate the forces as well as the stiffness. So that's the idea. So here, because we don't know the deformation yet, we can only work with the stiffness and also the matrix in the undeformed configuration. So basically, the U matrix here will be a bunch of zeros. So that's exactly what we have here. Okay, so now I have the stiffness matrix. I can come up with the applied forces. It's a 0 vector, 9 by 1. And on the 6th index, which is the second node in the z direction, I have an upward force of a unit 1. So this is exactly what's being defined here. So before we going further forward, there's one thing we do hope to discuss a little bit here, which is how do we modify the matrix and also the forces so that we can consider the boundary conditions, right? If you look at here, there is ijk node, but in this particular example, we will actually force the ith node and the kth node to be not moving. So there's going to be a support there. They cannot move in any direction. And then also because we want to keep this to be a simple a 2D problem, so we also don't want the jth node to be moving in the y direction, so that's perpendicular to the screen. So how can we do that, right? The most common method that people could use is to fill a large number to the appropriate location of the stiffness matrix. So we modify the stiffness matrix. So if you try to Google, let's say do a search about how do I modify stiffness matrix for support conditions, this is probably that first method that will pop out from the search result. You can read the Wikipedia, it will give you a lot of more information if you're curious to learn how to do it. But basically what will happen is, let's say I have a stiffness matrix. So in our case, this will be 9 by 9 because I have 3 nodes. And for each of the diagonal, the first 3 of them, it's associated with node I or the first node. The second 3 of them is associated with the node J or the second node. And then there's going to be the third 3 diagonals, which would be associated with node K, and that's this node here. So we'll first create this large number. So large number is 10 to the power of 6 for this particular example. That's going to be large enough. And what I will do is I will try to fill those indices where I want to restrict the motion. So for instance, I don't want node I to move at all, and therefore I will fill a very big number in these diagonals. So basically the idea here is that because the diagonal stiffness is so large, it's going to be hard to move it. Even if you apply forces to the structure, this node will most likely don't move a lot because of that extremely large stiffness in the diagonal. So that's how the system will work. And the same thing for node K, right? I will gonna get a very large stiffness to feel there. So this is node I, node J, and then the bottom will be node K. And this is my stiffness matrix. So that's still not enough because I still hope to have the node J in the Y direction. I want to, excuse me, that's not where I want to go. I want to restrict the motion of my node J in the Y direction. And this is done by filling the big number to be also here in the fifths and fifths location. And this is done using this function called adjust K, adjust stiffness matrix. And it's basically changing the diagonals to be this large number for the selected support location. So in addition to the stiffness matrix, we also need to do something to the applied force. We want to adjust its format. So the idea here is that for the applied force, again, I have a 9 by 1 applied force, right? So the first node, there's going to be 3 components. The second node, another 3 forces, and then the third node would be another 3. So that's the structure of my applied force vector. What I can do here is let me try to adjust it and make sure that whenever I have a support, the applied forces will automatically get a 0. So why do I do that, right? So suppose that your node is a support and there's a force applied to it. These applied force will never go into the structure. It will be directly taken fully by the support, right? That's the concept. So I actually don't need them. So when there's applied force, I just throw them out because they're already taken care of by the support condition. And therefore, since my first node is a full support, is restricted to move in both X, Y, Z direction, I make the 1, 2, 3 index in my force vector to be 0. And then the same thing for the 7, 8, 9. These are support. They directly take all the load. So when I send the load into the structures, those are 0 already. So that's why 7, 8, 9 is 0. And then also because we do not want the second node to be moving in the Y direction, this one is 0. So this is the force vectors operation. So as you can see, when we have an applied force, it's basically a bunch of zeros except for the second node in the Z direction. So in this case, it would be the 6th index. That's going to be 1. All right. So now that I have these applied force and also my stiffness matrix in the linear solver, what we're going to be doing is we just get the stiffness matrix, get a backslash, get the applied force and solve for that linear deformation, right? So that's basically this equation here for the linear solution method. So this is what we've been doing since our undergraduate, so hopefully you're not too unfamiliar with it. The only thing I want to point out here is again, doing the inverse in a computational world is not very efficient. We typically want to avoid it. So instead of using, inverse of the stiffness matrix and then multiply that with the applied force, we use backslash, so solving the linear system of equations. If you want to learn more about why we're doing these, you might want to consider taking the numerical linear algebra class. And from there, you will get more knowledge about some of these more detailed formulations here. Even if you do the inverse here, your life is still good. So, the computation right now is so fast to the point where if you're dealing with a reasonably simple structure, you actually don't need to worry too much about optimizing your code for fast computation. So we're actually born in it's in a fantastic era, right? That's the bad thing. The cell phones are more powerful than the computer we use to land human on the moon. So it's a good era to be alive, right? And so we already have this. So we found the linear deformation using the method we've been learning since undergraduate, and let's see what we got, right? So I have the U-linear. I want to plot the deformation. So the upper class X means the undeformed node for IJK node, And then for the deformed node, it's going to be the upper class x, the undeformed, plus the u linear, which is the one we just solved, right? And the smaller lowercase would be those deformed configuration. We plot the original bar location, and then we plot the deformed bar location, and we also create that big marker for the node, and this is the result we get. This particular node 2 got moved upward by unit 1, right? That's the result we solved. So looks good, or well, maybe not so good, right? So intuitively, I know this system is not in equilibrium, right? How do I know that, right? So we're looking at this type of deformed configuration, right? There's a force of 1 going upward. I know this vertical bar is still vertical. It has a force going downwards. And then I know that there's going to be a force along this originally horizontal bar, BH. And now it's no longer horizontal. And because of that, there is a force component in the x direction. And that force is nothing to balance it out. Right? So this thing cannot be at equilibrium. And let's verify that by finding the current force vector using these linear solutions deformation we found, right? So basically we can, with our bar class, the way we solve for the current force is we input its nodal coordinate and also the deformation, right? That's something we previously had used in using the equations we developed in the section 6 and also section 5. So if I find the global force vector using this solved deformation, the 6th index, or basically the second node in the z direction, the force I should get is 1.29, so 1.3 Newton. This is 30% larger than the actual applied forces, which is 1. So there's a 30% error there. There's a very large unbalance between the solution we found versus the applied force, and that's not good. Um, because the system is not in equilibrium, we're not satisfied with these deformation we just found. So what can we do? We want to use the nonlinear solver. We want to update the solution. So the Newton-Raphson method is that one method that is pretty good. It's usually one of that go-to method people use to attack a problem like the one we just see. So the basic formula of the Newton-Raphson is shown in this particular figure here. It's a little bit busy, but let me briefly explain that, what's happening. So what we're going to be doing is instead of directly applying a large force, we first break that large force into multiple small increment, delta F. And within each of the incremental forces, we repeat this linear solver, this linear solution over and over again. We keep updating the deformation using our unbalanced forces until that we find a solution where the unbalanced forces is low enough. So usually it's represented using a figure like this, where you can see the solutions it finds somewhere. It's a little bit far away from the ground truth, so I keep iterating, updating it with this little incremental step, iterative steps in the zigzagging curves, and until I find that final result. So that's what's going on here. So it's a little bit abstract if you just look at these figures. So let's keep doing these in some more realistic setup. So for this case, let's work on that two-spring problem again. So what I would do for the increment, I will break that 1 Newton into 2 steps. So each time we're going to apply a 0.5 Newton forces to the node. So try to do the first iteration using the linear solver. So at this point, for the stiffness matrix, the current deformation matrix is still 3 by 3 0. And we also want to create a vectorized version of that matrix. So basically, it's reorganizing the 3 by 3 into a 9 by 1 vector to help us run the code. And the stiffness matrix is generated using this zero deformation for the first steps. And then we adjust the stiffness matrix, adjust the applied force, and let's do the first steps. Let's try to see what will happen, right? So this is just like a linear step, but with the applied forces being reduced by half, so be reduced by 0.5. And so this is the deformation, the current vector. We update that with the du. Du is that deformation step we solved using the linear deformation. And let's try to plot it and see what we've got here. So not too surprising, right? It's still a linear step. And this node is put upwards by 0.5 because I'm cutting down the force by half. So originally, this 1 Newton force will bring this node up by 1 with 1 deformation. Now I got 0.5, right? But still the problem is still there, right? This node is only moving upward. This horizontal bar is stretched and it's gonna generate some unbalanced force in the left direction. So we can see that in the 6 index of the force vector. So basically in the z direction force, it's not balanced out perfectly. It's still there's going to be 10% of error there. And the most significant one is this unbalance. So we can we can we can find the difference between my applied forces and the internal forces solution, which is recalculated using the current, this updated deformation. And you can see that the biggest imbalance actually happens in the x direction, right? That's what we've been pointing out. So there is a 0.1 Newton of forces in the x direction that's very largely unbalanced, and that's primarily because this horizontal bar is now stretched due to the large deformation, but the node is not moving left to compensate for the forces that the spring is generating. So what do we do? The thing we can do here is we just reiterate the process, but this time we start from this new deformed configuration. And the force we're going to be using is the unbalanced force we just solved by subtracting the internal forces from my applied forces, right? So this is the unbalance. That's the force. And we reassemble our stiffness matrix at this configuration. This is what's been done. We adjust the new stiffness matrix in this new configuration, and we adjust the unbalance, and we do another linear step. So du is the u unbalance backslash with the stiffness matrix. So inverse of the current stiffness matrix and the current unbalance, we find a step to update our current u. So the current u is the current u sums that du. So you just add this additional step to the u solution, the deformation solution we have, and that's reshape it to the 3 by 3 and then plot it here. Okay, miraculously this node is moving leftward. That seems to be that's a good sign, right? That's one of the big complaint we say when we just look at the linear solution result, right? So this is moving the right direction. It's a good thing. So at this point, the solution is already getting much closer to what we want it to be. So what we hope to do eventually is to set up a while loop or a for loop to keep repeating what just happened in these boxes over and over again until the imbalance is a very small value. Okay, so that's what we hope to do. So we can actually check the imbalance here, balance, and let's try to output that result before I jump into the next section and see what do we have. Oops, I misspelled it. Balance. Right, you can see that the forces are still there. Oops, I didn't update that with with these computation here. And I'm gonna need to update my internal force also with the U current. So this will give me the new unbalance. Right, so look at the magnitude of this new unbalance. It's one digit smaller than what we used to have, right? Previously, this unbalance is very large, it's zero point 0.1 Newton, but now through one step of iteration, this unbalance is rapidly already dropping to zero point 0.01. So the nice thing about Newton-Raphson is that it's a second order method. It converges very fast. So in the following set of a code, what I hope to do is to set up this for loop or while loop to do this process over and over again. And my goal is to make my remaining or the unbalance to be smaller than 10 to the negative of 6. So that's my goal. So the R here is essentially it will be calculated as the norm of my displacement. So the step of displacement coming out from the imbalance. So when these deformations, so basically the adjustment I need to make to the deformation is small enough, I can call it a good solution. So the rest of the code structure is identical to to what we have here in this box. And after that, if I keep running it, let's stop that and keep running it. We're gonna reiterate for 7 steps. And let me actually also let me also output the residual. So you can see that this residual, it drops quite dramatically, right? It starts from a pretty large number, but it quickly drops to a value that is smaller than 10 to the power of negative 6. And that's when the algorithm say, okay, now we're good, we can stop. So the final result is these. As you can see, it's actually not too different from what we have here with just one iterative steps, right? So, but still, it brings us much closer to the solution to actual ground truth more numerically. Although visually, with eyeball accuracy, the one step is already enough. So let's check how well we do. Right, so I have the internal forces solved in this for loop. I have the applied forces, which is zero point 0.5 Newton. That's what we've been doing. And the internal forces do matches that from the applied forces very closely for, let's say, 4 digit here. So this is exactly indicating that we obtain that equilibrium configuration we want to find. Okay, pretty good. We've finished the first step, and let's work on the second step, which is increase the applied force from zero point 0.5 Newton to 1 Newton and go through that iteration again. So let me also actually print this result out so that we can see how fast these residuals start dropping. It starts with 0.3 and it quickly drops to uh, a value that's smaller than the 10 to the power of negative 6. And I can plot this result. So this time you can see the node got dragged leftward quite, quite a bit compared to the linear solution, which is what we have here, right? So this node got dragged leftward so that we have the forces balanced out. And when I compute the second node's force in the z direction, I get 1. So it's accurate to what I should have, and it's the same as the applied forces. It's indicating that the system is exactly in equilibrium. That's the goal that we hope to get. So that's basically Newton-Raphson in a short description, a brief summary of the Newton-Raphson method, and in reality, because the mathematics of Newton-Raphson is still not fully understood. Mathematicians have not yet figured out what's the exact equation to guarantee that the Newton-Raphson will give you a converged result. We do need to do some play with the setups, say how many steps we break the force into, and what's the residual, say, to so that we can get a converged result. So there's a little bit of trial and error when you're using this method, and that's all because the mathematicians have not yet figured out the rules, the exact rules that Newton-Raphson should follow. So what we know about the convergence is that if your initial guess of the deformation of within each of the Newton step is close enough to the ground truth, the Newton's method should give you a converged result. But there's no bound, any sort of a like a usable bound to learn about how close is close. So that's still a big unfinished work in the mathematics. So if you're interested, definitely check it out. Take some of the math class on topics like numerical linear algebra. That's where you will get more information about the method like these. So finally, related to the references and related classes, in civil or in mechanical engineering, there's typically these nonlinear structure analysis method. Newton-Raphson is typically one of those second order method they will cover in the implicit method section. And then in the explicit methods, we typically would talk about Runge-Kutta, which is a family of nonlinear solvers that people can use to solve for the deformation of the systems without doing that in iterative steps to minimize the error. So those will be covering that class. And if you want to learn more about a implicit solver method, more specifically, I would highly recommend this particular paper by Lian et al. It's a very good paper published in the Applied Mechanics Review. It go over a unified mathematical setup for all the different methods that's like Newton-Raphson, its incremental iterative framework. It covers a bunch of variations of arc length method, which depending on whether or not the professor has time, may or may not get captured in the nonlinear structure analysis class. So, but then this is if you want to learn more about these different types of method, this paper I would say it's probably one of the best go-to places to learn about arc length, Newton-Raphson, displacement control, so on and so forth, and the variations of those methods. So with that, I hope this section 7 gives you a good enough introduction of the nonlinear solvers side so that we can keep moving on to talk about some other elements and the formulations we would be learning for solving the other more complicated active structures and shape morphing structures next time. So with that, thank you very much for your attention, and I wish everybody have a great rest of your day.